Welcome everyone. Today's lesson is entitled Trigonometric Functions of Any Angle. For us, it's time to move beyond the unit circle and right triangle trigonometry and talk about the 6 ratios in reference to any angle in circular motion. So lots of concepts and examples to explore over the course of this lesson. Hopefully I've laid it out for you in a nice coherent way. I guess time will tell. All right, let's go ahead and begin with the review at the top. Obviously, this just expands on what we talked about in the last lesson. So, starting with this, every angle has 6 ratios corresponding to it. Excellent. Now, moving on to the next piece. The values of those ratios are really based on 3 things. They're based on what I would consider the horizontal distance, and on the coordinate plane, that would obviously be x. The vertical distance, and on the coordinate plane, that would represent y, and the direct distance, which would be the radius, so r, as the point moves in circular motion. So we have our x value, our y value, and our r value. That's pretty lousy r here, but hopefully you get the idea. So x, y, and r on the coordinate plane, horizontal, vertical, and direct. All right, now, a very important note as we move forward here. So we've talked a little bit about this idea before, but I do want to elaborate on it. When we're talking about the coordinate plane, x and y can be either positive or negative based on the direction. In fact, that's how I'm going to start this. So if you would write that in there, x and y are either positive or negative based on direction. So if I move upward on the coordinate plane, the vertical distance, the y value would be positive. If I move down vertically, it's negative. If I move to the right, horizontally, that would be positive. If I move to the left, horizontally, obviously, that would be negative. But one big piece here. In the rectangular coordinate system, which is what we're working in, r is always positive. Highlight that if you could, underline that, whatever the case may be. But r is always positive. So x and y may be positive or negative, but r is always positive, and you'll see how this works with our ratios moving forward. All right, so now we've got our definitions, which we've already done on the previous lesson, I believe, but now it's time to go ahead and just put them on this one for reference sake. And I'm going to just give you a little visual on this. It's not going to be great because I am artistically challenged, but that's all right. So, you know, we've got our angle right there. Here's our point moving in circular motion, tracking that angle. And so our theta would be right in here. And bringing this on down, that means we've got, looking at that point, we've got our x value, our y value, and our r value. Excellent. And this point just continues to move in circular motion. As x, y, and r change, the values of our ratios are going to change, and that's what we're going to explore today. All right, but every angle, and here's our theta right here, has 6 ratios that go with it, and they're based on x and y and r. And so those defined and named. So sine is y over r. Cosine of our theta is x over r. So sine, vertical over direct. Cosine, horizontal over direct. Tangent, as we've seen from day 1, is y over x. So vertical over horizontal. And then the reciprocals come into play. Let me get the in the right order for us, just so they make pretty good sense. So the next one I would say would be cosecant. So cosecant of theta being the reciprocal of sine. So if sine is y over r, cosecant is r over y. Secant being the reciprocal of cosine. So if cosine is x over r, secant is r over x. And lastly, cotangent being the reciprocal of tangent is going to be x over y. So please, guys, box that up. Put a big asterisk by this maybe out here, whatever the case may be. Must absolutely, positively know those going forward. All right, those are our 6. So what we've done at this stage in our units with trigonometry is we've started from kind of the beginning. We looked at the unit circle because it's a very good visual representation of our 6 trig ratios. We looked at right triangles, also a great visual representation of them. But now we want to expand beyond this for any angle, and that's why these definitions hold from here on out. So, are these definitions consistent with what we've learned with the unit circle and right triangles? You're going to humor me for a second and just put the answer as yes, and hopefully I'll convince you in just a moment here. I'll try to be quick with this. I can get bogged down with this, but I'm going to try not to. So just thinking of the unit circle for just a moment. And if you would, draw a unit circle there. And what's special about the unit circle, of course, is that the radius is 1 unit. So that's why I'm going to put a little 1, 0 here as our initial point. And then an xy right here. Okay, so this is how we kind of looked at it from the very beginning, talking about the unit circle. And the idea, if you remember, on the unit circle, the sine ratio was y, right? Do you remember that? Sine of our t value. Let's put a little t right in there. The sine of the t value was equal to the y coordinate. Well, why is it consistent with this right up here? Because remember, the radius is 1 unit. So on the unit circle, if the radius is 1, then you're getting y over 1. If you remember on the unit circle, the cosine of t was x. Well, why does that work here when we expand? Because if you remember, in this case, cosine of theta is x over r. Well, on the unit circle, the radius is 1. That's why on the unit circle it was just equivalent to the x value. So trying to make a long story short rather than just blathering on about it forever and ever, I guess I would say this. Yes, absolutely, because on the unit circle, the radius is 1 unit. Okay, and if you sort of think about r value being 1 and putting it right in here, that's what we saw all the way through. Okay, great. Just quickly do it with the right triangles. Again, I don't want to get bogged down on this. And I'm going to go ahead and throw a right triangle just on the coordinate plane for just a moment, just so we can see the consistency factor. So if I have a right triangle kind of like that, and I have my acute angle right in here, I kind of think of this as, oh, well, this is the opposite side to the acute angle. This would be the adjacent side to the acute angle, and this, of course, would be the hypotenuse. And if I think about the way we defined our 6 trig ratios in a right triangle, remember, sine was opposite over hypotenuse. Well, think about it on a coordinate plane. Isn't this y and isn't this r? So opposite, hypotenuse. Cosine, adjacent, hypotenuse. X, r. You can see that right here, adjacent, hypotenuse. So again, just kind of a long story short, why is it consistent? Because in a right triangle, I would say the opposite is equivalent to y. And again, pardon my shorthand, just trying to get through this piece for us. The adjacent is equivalent to x, and the hypotenuse is equivalent to r. So again, why did I kind of put this up on the board here? Just so you can see that these definitions, they're not new in any sense. They're just an extension of the two representations that we've worked on previously. And I hope that makes sense for you. Okay, I'm going to move on to my next board. And yeah, it's not just a matter of can you tell me what the sine of pi over 3 is, because at this stage you should be able to tell me the sine of pi over 3. But what does it mean at the end of the day? Not just, oh, I memorized it from the unit circle, but really what does it mean? Okay, so as soon as I see sine, sine is one of the 6 ratios, and what I'm asking for here is essentially this. So when I see sine, what I'm asking for is what is the y over r ratio, right? That's what I'm talking about when I talk about the sine ratio. What is the y over r ratio at pi over 3 radians? That's basically what that expression is asking us to evaluate. And so I'm going to try to be visual with this, just for the moment. I try not to take too long on it. So I think of, all right, well, pi over 3 radians is something like that. So from here to here is pi over 3 radians. All right, that's great. And the idea behind this is if you pick any point on the terminal side, and you were to calculate the y value over the r value, because that's what sine represents, those two together, y over r, then it's always the same number. So I picked a point, y over r, okay. Could I have done that here? Y over r. Could I do that? And think about this. This is an array, right? So this expands forever and ever and ever. So could I pick any of the infinite points on this terminal side, calculate the y over r, and always get the same number? Yes, that's the idea. The ratio stays the same, and we've seen this time and time again. Okay, so well, what is the y over r ratio at pi over 3 radians? Well, should look familiar. Root 3 over 2. Excellent. Next one, cosine 3 pi over 4. What is it actually asking? Not just, hey, have you memorized this, but what is it asking? So cosine of 3 pi over 4, it's saying, what is the x over r ratio at 3 pi over 4 radians? Good, so again, I'm trying to just provide a little meaning here for us. And so in this case, I'll try to be quick with my visual on this. There's 3 pi over 4 radians, right? Okay, and so if I pick any point on the terminal side, cosine is x over r. So what I'm looking for here is the x value to the r value. And again, direction matters. Do you notice for the x value, I'm going to the left. So that'll be negative. R value is always positive, so I have a negative divided by a positive. And when I do that, I'm always going to get a negative number. Negative divided by positive is negative. And so in this case, if you remember, it should be negative root 2 over 2. So it's basically saying if I take this value, divide it by that value, I will always get negative root 2 over 2. And not to belabor the point, sorry, but could I have done that here? Could I have taken this x divided by that r, and would I have gotten the same darn thing? You bet. Cool. Next one, tangent. So what is the y over x ratio at 7 pi over 6 radians? All right, so first and foremost, 7 pi over 6. Yeah, right there, give or take. So here's our theta, 7 pi over 6 radians, and I pick a point. Excellent. And tangent I think of as y over x. And notice what we have here, everybody. I have a negative y because I'm going down. I have a negative x because I'm going to the left. Negative divided by negative is going to give us positive. And if you remember correctly, this was the root 3 over 3, and it's positive because I have two negatives, one divided by the other. And again, I'm so sorry for belaboring the point. Could I have done this anywhere? Can I have done that y divided by that x and still gotten that number right here? Absolutely. Anywhere, any of these infinite points on that terminal side gives me the same value. And that's what trig is based on. It's all based on the concept of that ratio. Okay, so again, I hope that clears up some things or really drives home sort of the meaning of it. All right, so example 2 is just about getting familiar with those 6 ratios, and again, should know them defined very quickly. All right, so I'm going to go ahead and get started. It says find the 6 trigonometric functions of theta if point -2, 3 is on the terminal side of theta. So coordinate plane, everybody, if you would. And -2 on the x, +3 on the y. That is a point on the coordinate plane. And what it is saying here, it is a point on the terminal side of an angle. Now, think about it. Here's my initial side. Here's my terminal side now going through that point. This should kind of make sense from what we've been talking about, but there are an infinite number of ways to rotate from here to here. So I could just rotate counterclockwise that way, I could rotate clockwise that way, counterclockwise once around, or twice around, or 1,000,000 times around. There are an infinite number of thetas that would give us a terminal side from here. Now for our purposes, I'm just going to go ahead and rotate it from there to there and call that theta. But remember, that is just one out of an infinite number of thetas that would produce that terminal side right there. But for our purposes, I think it'll work. Okay, so I guess first and foremost, as I kind of look at this, since I have the point, that's your x, that's your y. The only thing I'm missing is r, right? So what we have found, and this kind of brings up one last piece from the last lesson, Pythagorean theorem, x squared plus y squared equals r squared. Please do not forget that. Make sure you do have that calculation in your mind. X squared plus y squared equals r squared. And in this case, I've got -2 squared plus 3 squared. Actually, I don't need the parentheses on the 3, but that's all right. Equals r squared. And so I get 4 and 9 make 13. So r squared is 13. Now remember, I've always kind of taught you this as when you undo square an equation, you're supposed to take the positive or the negative. Well, actually, you're supposed to take both, the positive and the negative. In this case, you're only supposed to take one or the other. So just want to highlight one thing. When I do r is always positive. So just without blinking an eye, everybody, r is always positive there. So r is root 13. Okay, now I probably shouldn't have boxed that up. Maybe erase your box if you would, because that's not our final answer, of course. But now that we have x and y and r, we're off to the races. So everybody, sine of theta is just y over r. So this would be 3 over root 13. Now again, if you don't mind, rationalize, and I'm going to sort of be a little quicker with this if that's all right with you. But this would be 3 root 13 over 13. Cool. Cosine of theta. Now we can get in a nice rhythm with these. Is just x over r. So that would be -2 over root 13, which again, if we rationalize, is -2 root 13 over 13. Tangent of theta, okay, is y over x, so 3 over -2. And again, really what that just means is -3/2. So the negative can just go out in front if you want, doesn't matter. Positive over negative is just negative. All right, remaining 3. Cosecant comes next. I always look at the unsimplified version. So that would be this right here as opposed to the final answer here. If it was 3 over root 13, then in this case, everybody, it'll be root 13 over 3. Secant. And just flipping this. So if it was negative 2 over root 13, it's just negative root 13 over 2. Remember, if that's negative, the reciprocal is negative. Cotangent, it was negative 3/2, so now everybody, it's negative 2/3. And so remember, the premise is just very simple. Every angle has 6 ratios that go with it, and the values of the ratios are based on x and y and r. So this angle from here to here has 6 ratios that go with it, and these would be the numerical values of those ratios. Okay, good. Little concept here to explore. So the investigation, I'm going to go ahead and read it through. It says the sines of each of the 6 trigonometric functions in the 4 quadrants. I guess that's what we're looking at. Draw a coordinate plane and determine the sines of sine, cosine, and tangent in quadrants 1, 2, 3, and 4. And then obviously if we can do those, then we can talk about the reciprocals. All right, so here's what I'm going to ask you to do as a matter of fact. 2 coordinate planes. One right there for me. One right here for me. And in this one, if you would, can you write sine, cosine, tangent in each of these 4 quadrants? And what I'm going to ask you to do is just put a little positive symbol or negative symbol for each of those based on the definition. So we know sine is y over r, cosine is x over r, tangent is y over x. So take a moment if you would, pause me please, and fill in all 12 of those. I'm going to do this in just a sec, and we'll see if you went 12 for 12. All right, well here I go. So in the first quadrant, sine, which is y over r, positive y over positive r. Positive over positive is positive. Cosine, positive x over positive r. That's positive. Tangent, positive y over positive x. That's positive. All right, I'm hoping you're 3 for 3. Now let's move into quadrant 2. Quadrant 2, sine, so positive y, because I'm going vertical, right? Can you see it now? Positive y over positive r, it's positive. Cosine, quadrant 2, guys, so we're going to the left, so negative x over positive r. Cosine's negative. Tangent, so we have a positive y over a negative x. Positive y over negative x is negative. All right, who's 6 for 6? Next one, sine. So this would be now a negative y over a positive r. Negative over positive is negative. Cosine, negative x over positive r. So remember, if I'm in the third quadrant, I'm going to the left. So that would be a negative x. R is always positive, so negative over positive is negative. And tangent, negative y over negative x, that's always the hard one, is positive. So tangent is positive in quadrant 3. Anyone 9 for 9 at this stage? Let's see if we can go 12 for 12. Sine, negative y over positive r, negative. Cosine, this is a good one. If you notice, if I'm in quadrant 4, cosine is going to be positive because I've got a positive x over a positive r. And lastly, tangent, negative y over positive x, negative. So here's what's sort of interesting about this. If you notice, in the first quadrant, all of them are positive, of course. But after that, do you see that only one out of the big 3 remains positive? In quadrant 2, it's sine. In quadrant 3, it's tangent. And in quadrant 4, it's cosine. And so that's how we're going to go ahead and put that together in our second one right here. So all positive in quadrant 1. Out of the big 3, only sine is positive in quadrant 2. In quadrant 3, tangent's the only one that's positive. And in quadrant 4, cosine's the only one that's positive. And there's a little mnemonic device to kind of remember this. So all and sine and tangent and cosine as we go 1, 2, 3, 4 around. So you ready for it? Again, it's kind of stupid, but it works. All students take calculus. Remember that? And now you can remember this. All students take calculus. So what that means, all are positive in the first quadrant. Sine out of the big three is the only one that's positive in the second. Tangent's the only one that's positive in the third. Cosine's the only one that's positive in the fourth. Hope that makes sense. All students take calculus. All sine, tangent, cosine. All right. So let's do an example to kind of back that up. Example 3. All right, very good. So, should know these now. So in this case, if I can tell you some information about theta, you can tell me where theta is. So you ready for it? Let's do A and then let's do B. So if tangent of theta is less than 0, and if it helps you, everybody, less than 0, what that means is that's negative. Less than 0 is negative. Greater than 0 is positive. So if tangent of theta is negative and secant of theta is positive, which quadrant are we in? Okay, now, to be honest, that's great right there, but as soon as I see secant, what I'm really thinking is cosine. So write that above. Remember, if secant is positive, then cosine has to be positive too. So I just do that myself. Even though this is what's going on, this is what I'm thinking. All right, so now if tangent is negative and cosine is positive, where are we? Well, I'm going to work off to the right here, I guess, and draw myself a little coordinate plane. And let's just deal with this right here. It's saying tangent of theta is negative. So which quadrants would we have a negative tangent ratio? Well, remember, all are positive here, tangent's positive here, so tangent is positive in these two, meaning tangent is negative in this one and this one. That's where tangent is negative. So already, just from this piece of information, everybody, I've narrowed it down to either quadrant 2 or 4. Now, out of those two quadrants, either 2 or 4, which one of those is the cosine ratio positive? So is cosine positive in this quadrant or this quadrant? And I would make the argument it's got to be quadrant 4. So the answer is quadrant 4. So if you notice, what's going on here is this piece of information narrows it down to 2 out of the 4 quadrants, and this one narrows it down to 1 out of the remaining 2. Love to see if you can do B by yourself, but if not, happy to walk you through. So cosecant is negative, cotangent is positive. Where would we be? All right, well, truth be told, as soon as I see cosecant, what I'm really thinking is sine. And as soon as I see cotangent, really what I'm thinking is tangent. All right, so let's start out with this piece of information first. It's saying the sine of theta is less than 0, meaning sine of theta is negative. So where would we see a sine ratio that is negative? So remember, all students take calculus. All are positive. Sine is positive. So up here, sine is positive. Down here, sine is negative. So those are just check marks saying it could be in either 3 or 4 at this stage. Sine, negative, down here. Out of those two, which quadrant would I have a tangent ratio that's positive? That's what this is saying right here. Tangent is positive. So would I have tangent positive here or here? All students take. There we go. So as we saw, tangent is positive in 3. And so we're in quadrant 3. All right, guys, I hope it's making sense. I'm going to go right into example 4, everybody. So the first order of business, before we answer this problem, which says find the values of the remaining 5 trig functions, because I gave you one of them, where the heck are we? Which quadrant is theta in? So as a matter of fact, you might want to state that to yourself. Which quadrant first? So where are we going to draw? And that's actually the second piece, as I have it on my paper, and I'm going to write it here. So draw a diagram. Man, there's so much of this drawing coordinate planes in trigonometry. So cannot stress that enough. So once we figure out which quadrant, we're going to draw a terminal side in that quadrant. Okay, so now let's go with our information. Sine of theta is equal to negative 5/13. Well, forget the 5/13 part for just a second. What I know is that the sine of theta is negative. Okay, and the cotangent of theta is positive. So first of all, I start with this. You know, I've got my coordinate plane. I'm going to go ahead and get my coordinate plane ready. So sine of theta, I just saw is a negative number. So what that means is I'm either in 3 or 4, one of the two. Okay, now I need more information because I don't know if it's in 3 or 4 just yet. So then I go to this, and I say, oh, cotangent of theta is positive, which, just like we saw in the last one, that means tangent is positive. And out of 3 and 4, which is tangent positive and cotangent positive, it looks like we're in quadrant 3. So based on this information, a negative sine ratio and a positive cotangent ratio, I'm going to be in quadrant 3. Now, you can draw anywhere in quadrant 3. If you get a little better with these numbers, you'll draw them, I don't know, potentially in a better place in the quadrant, but it's irrelevant. Go anywhere in quadrant 3. Pick a point on the terminal side. And we always go to the horizontal axis, always, always, always. And if you notice, when I go to the horizontal axis, I've created what's called a little reference triangle right in here, which has an X, and it has a Y, and it has an R. Perfect. Now, in this particular case, do you notice, and write this please on your paper, as soon as I see sine of theta equals something over something, what that really represents is Y over R. Let me repeat that one more time. Sine is Y over R. So what I can do is start labeling, in terms of X, Y, and R, I can at least label 2 of the 3. Now, we have to be careful of signs. So I'm going to start with the R because that's always the clearest. R is always positive. So I know that the R part of this is positive 13. No question about that whatsoever. Now the Y could be positive or it could be negative, but direction matters. You'll hear me say that a lot. So in this case, if you notice, because I'm going downward vertically, that has to be a negative 5 right there. So cannot stress enough, draw the coordinate plane, draw the terminal side, and let's label the 3 parts. In this case, I'm given Y over R, so I put the R there as positive 13, the Y there is negative 5. Now I need a little Pythagorean theorem to go ahead and get that. So x squared plus negative 5 squared equals 13 squared. So I get x squared plus 25 equals $169. X squared equals 144. And then I'm going to pause for a second. Now here's where we're going to be careful. So I've taught you in the past, when we undo a square in an equation, we have to take both the plus and the minus. Well, obviously, guys, I can't take both. It has to be one or the other. So the question is, from here to here, do I want this as positive 12 or do I want it as negative 12? And because direction matters, and I'm going to the left, I take the negative. That is a huge piece, guys. That's why the coordinate plane is so important in your drawing. Don't just draw triangles. Draw the coordinate plane too. Because I have to come from the origin. I have to go to the left. And so that's why it's negative. All right. Now that it's labeled, because this is, to me, most of the battle right there. Once it's labeled, we're ready. So I'm just going to go ahead and write the answers. Sine of theta is just y over r. I guess that was already given, huh? It did say 5 and the remaining 5. But all right, I put the 6th one that was given there. No harm done. All right, cosine of theta, x over r. It's just negative 12/13. Look how fast we can do these. Tangent of theta is y over x, negative 5 over negative 12. Negative over negative is positive, which we knew it to be the case, right? If we're in quadrant 3, tangent is positive. Cool. Let's get the reciprocals. Cosecant of theta is just negative 13/5. Secant of theta is negative 13/12. And lastly, cotangent of theta would be 12/5. Every angle has 6 ratios that corresponds to it. Here's your angle right here. If you want to think about it in just the primary rotation around, infinite number of thetas, though, to get from here to here. But that angle has 6 ratios that go with it. These are the numerical values of those 6 ratios based on the information. Fantastic. All righty. So as I've been saying all along, it's not just a matter of memorizing or visualizing particular values, particular ratios of our angles. It's also understanding the behavior of especially sine and cosine as the angles increase or decrease, for that matter, basically as the angle measures change from 0 to 2 pi. So let me read this more specifically so we can get into it here. So it says, describe the behavior of sine and cosine as angle measures increase from 0 to 2 pi. So kind of our primary rotation around. On the given intervals, decide if values are increasing and decreasing, and also determine the beginning and ending values. Okay, so I came up with just a little visual on this. Let me see if I can pull it up for us. All right, something like that. And I'm going to come over to my computer here for a moment, and all I want you to do is we're going to just take 60 seconds. And now this should be at the initial point, so the sine ratio, by the way, should be 0. It's just not exactly on the point, but it's good enough. And the cosine ratio should be 1. So what I'm going to basically do, everybody, is I'm just going to take this point, and I'm going to go around once, and then pause for a moment. And I just want you to get a sense of what's going on with these values, positive and negative, and are they increasing and decreasing, and what they max out to and what they drop to in terms of a minimum. All right, so you ready? So we start here, and I'm going to go around. Just keep an eye on the sine and cosine. Notice the sine ratio is going up. Cosine ratio is going down. Both positive, though. Cool. We come up here, and do you see, and again, if for some reason it's just, this should be 0 at this stage, but notice we hit the top, and the sine ratio is 1. Okay. Notice now cosine turns negative, sine stays positive. But take a look, everybody. See the behavior of these values? Sine's coming down to 0, cosine going down all the way to -1. Excellent. Third quadrant, notice sine and cosine both negative. So sine dropping all the way down to -1, cosine coming back towards 0. Lastly, fourth quadrant, notice sine is negative, cosine's positive. So this is kind of nice. You get a real good visual representation of everything we've kind of talked about. And then we come on back, sine getting closer to 0, cosine getting back closer to 1. All right, and I could obviously go around and again and again and again. All right, I'll stop the madness. But I think that gives us enough. So with that being said, let's fill this in. So what we saw, and again, you can go back and just rewind and repeat that, that demonstration if you want. But time is a little bit of the essence here, so I'm going to rush through this piece. So first of all, sine. We saw in the first quadrant increases from 0 to 1. That's the behavior of sine in the first quadrant. Whereas cosine decreased from 1 to 0. Again, we saw this in right triangles as well, by the way. Second quadrant, we saw sine starts to come down from 1 back to 0. Whereas cosine went into the negative, so it decreased from 0 down to -1. Third quadrant, sine starts to go into the negatives. So from 0 all the way down to -1. Whereas cosine now starts to increase because we were at a minimum at -1. Now we start to go back up. So from -1 back up to 0. And again, this is really just about the behavior of sine and cosine as the angles change. So increasing from -1 to 0. And lastly here, increasing from 0 to 1. And again, feel free to rewind to that visual demonstration just so you can see these a little more in action. But you can start to see we hit sine and cosine maximums. The ratio can only get up to +1 and can only get down to -1. We're never going to see sine ratios above 1. We're never going to see cosine ratios above 1. And we'll never see them below -1 based on our definitions. Cool. All right. Now, this is just a prelude into the next lesson, which happens to be entitled Reference Angles. And I'm going to be just super fast with this, just again as kind of an introduction to what you're going to see tomorrow. So let me read it. We will evaluate trigonometric functions of positive angles greater than 90 degrees and all negative angles by making use of what's called reference angles. Now guys, I underlined it, but maybe somehow highlight this on your paper if you can. Reference angles are always acute and always positive. Always acute, always positive. And it's just a different way to kind of talk about these ratios outside of using maybe the unit circle, okay? So again, I'm not starting from scratch. I'm not reinventing the wheel, but we're going to see this in tomorrow's lesson using this idea of reference angles. Okay, anyway, reference angles, always acute, always positive. Here's what you're going to do for me. So, first of all, in degrees, can you write this on your paper? So that means it has to be in between 0 and 90 degrees. In radians, what that means is it has to be in between 0 and pi/2 radians. And remember, pi/2 is roughly about 1.57 units. Not exactly, but roughly. So knowing that reference angles, and you don't know anything about reference angles just yet, that's okay, have to be in degrees between 0 and 90, radians between 0 and pi/2. Can you take a moment and answer all 8 of these? Okay, go for it. That's a yes. That's a yes. That's a no, too big. That's a no, too big. Pi/6, is that in between 0 and pi/2? You bet. Is 1.2 radians in between 0 and pi/2? Yeah. So, is 2 pi/3 in between 0 and pi/2? No. And by the way, I see a little typo here. Call that H. And can a reference angle be negative? No, absolutely not. All right. So I think I had a bigger problem set. That's why I guess I erased one and never changed the letter on it. So call that H. All right, perfect. And lastly, since this is going to come up tomorrow, if you would take a moment. And what I want you to do is just draw theta. in the second quadrant. We're going to do this in all the quadrants tomorrow, I think. There's a nice looking theta from there to there. Now a reference angle, if you would, is going to be this little guy right in here. And so what I want you to do on your paper, if you can please, is pick a point on the terminal side, and we talk about this all the time. Always go to the horizontal axis. Okay? Perfect. And the reference angle always, always, always will be in between the horizontal axis and the terminal side. Again, horizontal axis, terminal side. And so if you would, let's just draw that, and then we'll wrap this on up. So theta prime, that's our reference angle, by the way. Sorry about that. Reference angle, and it says it right here, is always between the terminal side of theta and the horizontal axis. So never the vertical, guys, never the vertical. Okay, now there's not a whole lot of context for these reference angles. It is just, again, as I said, an introduction to tomorrow's lesson. All right, I'm going to wrap it up right there, everybody. Thank you so much.